a typical carbohydrate, which is the main source of energy in our body. Whatever we eat is digested and it is converted into glucose, and from that glucose we get energy to perform our functions. So in this video we will focus on glucose, which is a monosaccharide, and we'll study its properties, its reaction and other many things about glucose. So let's start. Preparation of glucose. First of all, the first method is boiling sucrose, that means cane sugar, with dilute HCl or H2SO4 in alcoholic solution. This refers to hydration of sucrose. Actually, sucrose is a disaccharide which is formed by a combination of 1 unit of glucose and 1 unit of fructose. Glucose and fructose combine together to form sucrose. So if we break down sucrose, we do hydrolysis of sucrose, we will get glucose and fructose. The first method is this. Sucrose is actually reacted with HCl, alcoholic HCl or H2SO4 to form glucose and fructose. Next method is by boiling starch with dilute H2SO4 at 393 Kelvin under pressure, because starch is a polysaccharide which is formed by a combination of glucose units. So if we do hydrolysis of starch also, we'll get glucose, but the hydrolysis of starch is slightly more difficult because it is a polysaccharide, so we need to boil it with sulfuric acid. And this is how it is done. And similarly, we can obtain glucose by hydrolysis of cellulose also, because all these are formed by a combination of glucose units. Now this is the structure of glucose. If you can see from here, there are 6 carbon atoms, 1, 2, 3, 4, 5, 6, 1 aldehyde group, 1, 2, 3, 4 secondary OH group and 1 primary alcoholic group. So this is the structure of glucose. But the question comes, how did we know in very starting that what is the structure of glucose actually, because glucose was synthesized from food sources. So how we came to know that what is its structure? So glucose has been assigned its structure based on following evidences, and the first evidence is that it has 6 carbon atoms. It was observed using various techniques like X-ray and spectroscopy, that in the formula is this C6H12O6, that means it contains carbon, hydrogen and oxygen. And the next thing was when glucose was heated with hydrogen iodide, it resulted in formation of N-hexane, which is a straight chain hydrocarbon with 6 carbons. This indicates that there are 6 carbon atoms in, yes, a glucose molecule. Next is that when it was reacted with NH2OH or HCN, it resulted in formation of these addition compounds. This represents that there is a carbonyl compound present in, there is a carbonyl group present in glucose, because this is a reaction of typical carbonyl compound. When it is reacted with any ammonia derivative, it results in formation of, yes, something like we get this product, simple addition product with NOH. This is a typical reaction of carbonyl group. Similarly, the next reaction is also shown by compounds containing carbonyl group, and this is HCN. After this we get hydrocyanide. Here comes OH. H goes with this oxygen, and we are left with cyanide, which attacks here. So these two reactions, which are actually characteristic of carbonyl compound, represent that there is a carbonyl group present in glucose structure. And when it is reacted with bromine, it resulted in formation of an acid, gluconic acid. Now this represented that the carbonyl group is present at terminal position, and as it is present on terminal position, that means it is an aldehyde. So up to this we got 3 points. That first is that it has 6 carbon atoms, second is that it has a carbonyl group, and third is that the carbonyl group is aldehyde. And when we did acetylation, when glucose molecules was reacted with acid anhydride, it resulted in acetylation, and what we found that 6 acetate radicals got attached with with glucose. So this indicated that these were actually 4. When, let's say, this was the structure, CHO, CHOH, similarly CHOH, CHOH, 1, 2, 3, 4, CHOH, 1, 2, 3, 4, 5, and final was CH2OH. When acetylation was done, these 1, 2, 3, these 5 OH groups were replaced by acetyl group. This represents that actually there are 5 OH groups present in structure of glucose. Next is when it was reacted with HCN, that means when its oxidation was done, we got saccharic acid, which was the common product which we obtained from oxidation of gluconic acid also. Now this is the gluconic acid. When we oxidize gluconic acid, we get saccharic acid. It already contains a carboxylic acid group at one point, so that means the another terminal was oxidized to get this. Similar product was obtained, the same saccharic acid was obtained by oxidation of glucose also. This represent that there is an aldehyde group. Obviously there is an aldehyde group which would have converted into carboxylic acid due to oxidation, but at another point there is an OH group which is attached actually to a primary carbon atom, and then only it also got converted into the carboxylic acid group. So this indicates that there is presence of a primary alcoholic group in structure of glucose. And after all this, the only structure which is possible for glucose is CHO, one OH at this point, then this may be at this side or that side, then OH, 1, 2, 3, 4, 5, and finally. So this was the final structure assigned to glucose. Okay. Now there is an important reaction of glucose or any other monosaccharide that they undergo oxazone formation, and there is one thing that glucose and fructose both form same oxazone when they are reacted with phenylhydrazine. Now what happens when it is reacted with phenylhydrazine? Actually we have CHOH form groups, and finally CH2OH. When this was reacted with 3 molecules of C6H5 NH2, the compound was formed oxazone. And what is actually oxazone is, let's say we have this group, and then let's say our group. When this would be reacted with C6H5 NH2, we will get, with removal of a water molecule, C double bond NH, then phenyl group here. Similarly CH double bond N NHPH. There is an H another and then an R group. So this is actually OSA zone. Now the fact is that both glucose and fructose form same type of OSA zone, because the only difference in structure of glucose and fructose is that one is that in first the carbonyl group is present at terminal, while in second the carbonyl group is present in second carbon. Let's write their structure. The structure of glucose is this: OH, OH, another OH here, 1, 2, 3, 4, one here, and then CH2OH. While structure of fructose would be CH2OH, then a carbonyl group here, then OH group, another OH, CH2OH. Now they both differ from one another only at starting 2 carbons. But in OSA zone formation, both of these two are involved. So finally, when they are reacted with phenyl hydrazine, in case of glucose we get this product, and similarly in case of fructose also we get this product, because they only differ from one another by starting 2 carbon positions, and both of them are involved in formation of OSA zone. So they both form identical OSA zones. Now there is D and L configuration of glucose. We have already studied that the simplest carbohydrate is actually glyceraldehyde, and if in glyceraldehyde OH is present on right hand side, it would be L, it would be actually D, and if it is present on this side, it would be L. So a D and L configuration is assigned to every monosaccharide based on its structure with respect to glyceraldehyde only. DLN families are defined by orientation of OH group on the chiral carbon, which is farthest from the carbonyl group. So in this case, this is D-glyceraldehyde, this is L-glyceraldehyde. Okay, if I want to write the structure of glucose, just see CHO, then OH, another OH, OH, another OH, and this is CH2OH. Is this the structure? Yes. Okay, in this case, if it is D or L glyceraldehyde, D or L glucose, it will depend on the orientation of OH group, which is farthest from the carbonyl group. This is the carbonyl group, and 1, 2, 3, 4. We have 4, actually these 4 are chiral carbon, but the one which is farthest from the carbonyl group is this. So we will see the orientation of OH group in this carbon, and if it is on right hand side, in that case it would be D, and if it is on left hand side it would be L. So this is a D glucose, and if I want to write the structure of an L glucose, it would be like this: OH, then OH here, then one OH here, then one OH here, and CH2OH. And again these two are, yes, epimers, because epimers are those compounds which differ from one another only by orientation of groups at one carbon atom. So these two are epimers. This is D glucose, this is L glucose. Now solved example. There is a solved example. Glucose and fructose form, we have studied just now that glucose and fructose form same OSA zone. This is because they differ from one another only by, yes, starting 2 positions. In glucose this is like this, and then entire chain. In case of fructose it is like this, then entire group, and both of these are involved in formation of OSA zone, so they do not they form same OSA zone. Next is glucose reacts with excess of phenyl hydrazine to form, it is gluco-OSA zone, just like this: CHO, OH, then OH, then OH. This is D-glucose. When it is reacted with excess of NH2, NHPH, phenylhydrazine, it results in formation of, yes, this compound. And then it would be, yes, OH here, one OH here, then here, and CH2OH here. So this is the way glucose forms glucaosazone. Glucaosazone. So correct option is A. So students, we studied about glucose. We know it is a typical carbohydrate and we know what are its properties, what is its structure, and also its chemical reactions with many other compounds. We know that what is the reaction which is known as osazone formation. In our next video, we will focus on actually cyclic structure of monosaccharide and mainly glucose. Keep watching.